Welcome to your first semester of mathematical physics. Today, we are going to embark on a fascinating journey into the world of probability. We will explore three foundational distributions: the binomial, the Poisson, and the Gaussian. Whether you are flipping a coin, counting radioactive decays, or measuring the thermal noise in an electronic circuit, these mathematical tools are absolutely essential. They form the bridge between random microscopic events and predictable macroscopic behavior. Let us dive in and see how we can mathematically model the randomness of the universe. Let us start with our first major concept, the binomial distribution. Why does this matter? Imagine you are trying to predict the behavior of a system where particles can only exist in one of two distinct energy states. Without this distribution, we would have no reliable way to predict the overall behavior of such systems. The binomial distribution models any scenario where you repeat a simple yes or no experiment multiple times. For a process to be binomial, it must meet strict conditions: a fixed number of identical trials, complete independence between trials, and exactly two outcomes per trial, usually called success and failure. Because we are counting specific events, this is a discrete distribution, meaning you can only have whole numbers of successes, never fractions. Now that we understand what a binomial process is, let us look at its mathematical form. This beautiful formula calculates the exact probability of getting a specific number of successes. The symbol P of x equals k represents that probability. The variable n stands for the total number of independent trials you are conducting. The variable k is your target number of successes. The variable p represents the probability of success on any single trial, while 1 minus p is the probability of failure. The bracketed term, n over k, is the binomial coefficient, which counts how many different ways we can arrange those successes. Physically, if you increase the number of trials, n, the distribution spreads out. If you increase the success probability, p, the peak shifts toward a higher expected number of successes. This formula we just saw leads us to an important question. What is the average expected outcome? These two simple formulas give us the mean and the variance of the binomial distribution. The Greek letter mu represents the mean. This is simply the expected average number of successes if we repeated the experiment many times, calculated by multiplying the total trials, n, by the success probability, p. The symbol sigma squared represents the variance, which measures how spread out the possible outcomes are around that mean. If the probability p is exactly 1/2, the variance reaches its maximum possible value for a given number of trials, meaning the outcomes are as spread out as possible. Before we move on, let us see this with a concrete example. Suppose you flip a perfectly fair coin exactly 5 times, and you want to find the exact probability of getting exactly 3 heads. First, we identify our given values. Our total trials, n, is 5, our success probability, p, is 0.5, and our target successes, k, is 3. We chose the binomial formula because these are independent binary trials. We substitute these values into our equation. The combination term evaluates to 10, meaning there are 10 different sequences that give 3 heads. We multiply this by the probability of 3 heads and 2 tails. The final result is 0.3125. Physically, this means if you repeat this 5-flip experiment thousands of times, you will get exactly 3 heads in about 31% of them. Let us reinforce this with a more applied, real-world example. A factory produces components with a historical 10% defect rate. An inspector selects a random batch of 4 components. What is the probability of finding exactly one defective part? We treat each component as an independent trial, so n equals 4. A success here is finding a defect, so p equals 0.10, and our target k is 1. We plug these into the binomial formula. The combination term is 4 because the single defect could be any of the 4 parts. Multiplying the terms together gives 0.2916. This tells the factory manager there is roughly a 29% chance of finding exactly one defective part in this sample, which is essential for setting quality control thresholds. Now that we have calculated specific probabilities, let us visualize the entire distribution. Here, you are looking at a bar chart for a binomial process with 10 trials and a 50% success probability, like flipping 10 coins. The horizontal axis shows the possible number of successes, from 0 to 10. The vertical axis shows the probability of each outcome. Notice the perfect symmetry. The tallest bar is right in the middle, at 5 successes, which is our expected mean. As you move away from the center, towards 0 or 10, the bars get progressively shorter, showing that extreme outcomes are highly improbable. This visual perfectly captures how independent random events cluster around an expected average. This brings us to our second major topic, the Poisson distribution. Why do we need another discrete distribution? Imagine watching raindrops hit a single tile. You know the average rate, say 5 drops per minute, but the exact timing of each drop is completely random. The binomial distribution cannot handle this because there is no fixed number of trials. A drop could hit at any microsecond. The Poisson distribution is the mathematical concept that models these kinds of random, independent events happening over a continuous interval. It assumes an infinite number of possible trials, each with a very tiny probability of success. It is the ultimate tool in physics for analyzing rare events or random arrivals, like alpha particles emitted during radioactive decay. Now that we understand the Poisson concept, let us examine its elegant mathematical formula. This equation calculates the probability of observing exactly k events in our chosen interval. The parameter lambda is the heart of this formula. It represents the average rate of occurrences and must be a positive number. The symbol k is our target number of occurrences. The symbol E is Euler's number, a mathematical constant that naturally appears in growth and decay processes. The denominator is k factorial, which scales the result to ensure all possible probabilities sum perfectly to 1. Physically, if you increase the average rate lambda, the peak of the distribution shifts to the right, meaning you expect more events to happen overall. This formula reveals one of the most fascinating and unique properties of the Poisson distribution. Let us look at its mean and variance. The symbol mu represents the mean, which is simply equal to our average rate parameter, lambda. Amazingly, the symbol sigma squared, which represents the variance, is also exactly equal to lambda. This is a profound physical statement. It means that in a Poisson process, the spread or uncertainty of the distribution grows at the exact same rate as the average number of events. If you expect a very large number of events, the absolute variation around that expectation will also be large. This single parameter elegance simplifies many complex calculations in statistical physics. Let us apply this to a classic physics problem. A Geiger counter detects an average of 3 alpha particles per minute from a radioactive sample. What is the probability of detecting exactly 5 particles in a randomly chosen minute? We choose the Poisson formula because radioactive decay is a continuous random process with a known average rate. Our average rate, lambda, is 3, and our target, k, is 5. We substitute these into the equation. The term 3 to the 5th power represents the influence of our target number. The exponential term acts as a damping factor based on the average rate. Dividing by 5 factorial gives us approximately 0.1008. Physically, this means in roughly 10% of the 1-minute intervals, you will count exactly 5 particles, showing that such fluctuations are quite common. Let us look at another practical example to solidify this. A printed textbook averages 0.5 typographical errors per page. If a student opens to a random page, what is the probability it has absolutely 0 errors? We model this as a Poisson process over the continuous space of a single page. Our rate, lambda, is 0.5, and our target, k, is 0. We plug these into the formula. Any non-zero number to the power of 0 is 1, and mathematically, 0 factorial is also defined as 1. This beautifully simplifies our equation, leaving only the exponential term, e to the power of negative 0.5. The result is approximately 0.6065. This means there is roughly a 61% chance that any randomly selected page will be completely flawless. Here, we can visually analyze the Poisson distribution for an average rate of 3. Just like our radioactive decay example. The horizontal axis shows the number of events, and the vertical axis shows the probability. Notice how this shape differs from the binomial chart. It is not perfectly symmetrical. Because the number of events cannot be less than 0, the distribution is bounded on the left, creating a slight skew. The highest probabilities are clustered around 2 and 3 events, which aligns with our average rate of 3. As you move to the right, the probability of observing 6, 7, or 8 events smoothly decays toward 0. This visual perfectly illustrates how the Poisson distribution handles the frequency of random arrivals. We now arrive at the undisputed king of probability, the Gaussian, or normal distribution. Why is this so important? Thanks to the central limit theorem, the sum of many independent random variables will always tend toward a Gaussian shape, regardless of their original form. This makes it the ultimate mathematical bridge between random microscopic events and predictable macroscopic behavior. Unlike our previous distributions, the Gaussian is continuous, meaning it deals with variables that can take any real value, including fractions and decimals. If you measure the heights of thousands of people or the thermal noise in a circuit, the data will cluster around a central mean and taper off symmetrically, forming a perfect bell-shaped curve. It is completely defined by just 2 parameters, where the center is and how wide the bell is. Let us look at the famous equation that generates this bell curve. This is the probability density function of the Gaussian distribution. The symbol f of x represents the probability density at a specific continuous value x. The parameter mu is the mean, which dictates the exact center of the distribution. Changing it shifts the entire curve left or right. The parameter sigma is the standard deviation. Increasing it makes the bell curve wider and flatter, while decreasing it makes the curve narrow and sharp. The fraction in front ensures that the total area under the entire curve equals exactly 1. The exponential term contains the square of the distance from the mean, which guarantees that the curve drops off rapidly and perfectly symmetrically on both sides. Because integrating the Gaussian formula is highly complex, we often use a powerful shortcut called the empirical rule. Suppose exam scores follow a Gaussian distribution with a mean of 70 and a standard deviation of 10. What percentage of students scored between 60 and 80? First, we identify our mean, mu, as 70, and standard deviation, sigma, as 10. We calculate our lower bound by subtracting one standard deviation from the mean, giving us exactly 60. We calculate our upper bound by adding one standard deviation, giving us 80. Our target range spans exactly from one standard deviation below to one standard deviation above the mean. The empirical rule states that approximately 68.27% of all data falls within this exact interval. This is an incredibly fast way to estimate probabilities. Let us try a more advanced engineering example. A machine cuts metal rods with a mean length of 100 millimeters and a standard deviation of 2 millimeters. What percentage of rods will be longer than 104 millimeters and scrapped? First, we calculate the z-score to find how many standard deviations our target is from the mean. We subtract the mean of 100 from 104 and divide by the standard deviation of 2. The result is exactly 2. The empirical rule tells us that roughly 95.45% of data lies within 2 standard deviations. The remaining 4.55% lies outside. Because the curve is perfectly symmetrical, exactly half of this remainder lies in the extreme right tail. Dividing by 2 gives us approximately 2.27%. Let us visualize the Gaussian distribution and the empirical rule we just applied. Here you see the classic, perfectly symmetrical bell curve. The horizontal axis represents the continuous values, centered exactly at the mean, mu. The vertical axis represents the probability density. Notice the shaded region in the center. This area spans from one standard deviation below the mean to one standard deviation above it. As we calculated earlier, this specific shaded area always contains roughly 68% of the total probability, no matter how wide or narrow the bell is. As you move further out to 2 or 3 standard deviations, the curve approaches the horizontal axis but never quite touches it, representing the extreme tails of our data. We have covered a tremendous amount of ground today. Let us review the 3 most important ideas. First, the binomial distribution is your tool for discrete, fixed trials, where you only care about success or failure. Second, the Poisson distribution handles discrete, rare events happening randomly over a continuous interval of time or space. Finally, the Gaussian distribution is the continuous, symmetrical bell curve that governs variables taking any real value. Remember, these are not just abstract math equations. Thanks to the central limit theorem, they are deeply connected, serving as the mathematical foundation for experimental physics, quantum mechanics, and statistical data analysis. You now have the tools to mathematically model the randomness of the universe.